thank you for joining our GennFlex webinar. We want to talk about our holistic solution for training and education, and right now we're featuring our mini robot, which teaches beginning programming for robots. We have a holistic solution, and I really want to talk about how that evolved. GennFlex was born out of necessity to provide teachers a means to teach students how to program robots and use those with other automated devices. And the whole point in manufacturing and how you use this on the job is efficiency, right? Machine language, and how you use automation and automated systems to do a job better, quicker, more efficient, better economics. And schools do a phenomenal job already with their STEM programs and career technology programs, but the missing link is really how do they transition from what they learned in school to what they need when they go out on the job, whether it's engineering or as a technician. Things aren't exactly the same. They're simulated, the principles are all right, but they're not using that equipment. And so employers, when they're bringing these students in, almost have to retrain them again and saying, okay, it's great what you learned in school, but this is what we use here. And GennFlex thought, you know, what we'll do is we'll train our own. Before they were GennFlex, the founders did that, and they brought in, engineers, technicians, curriculum design people, marketing people. They queried the education marketplace to find out what do you need and what's our delivery system going to be. And they came up with a holistic system that includes curriculum from cradle to grave, basically. Students start out with beginning what they need to learn, with beginning programming and robots and other devices, on up to instructor certification and recertification and staying sustainable with open architecture and what these technologies do. But I don't need to ramble on about that. I'd rather have you listen to Mark and have him introduce you to how we begin this program with our Yaskawa Moto Mini.
All right, so this is for our education package using the Yaskawa Moto Mini robot. From a hardware standpoint, the cart is designed to fit through all standard 32-inch doorways. It's got a step-up transformer built in, so from a power standpoint, all it needs is a standard wall outlet to be powered. It runs on a YRC1000 microcontroller, which is a standard controller used by Yaskawa for industrial applications. It's got the Yaskawa Moto Mini robot, which is a 6-axis robot. It comes with teaching aids, such as a conveyor, a shunt gripper with different fingers that we supply. It's got a pallet, comes with cubes, a whiteboard, an I/O pendant, along with the smart pendant. It also comes with a safety sensor, which you can see down here at the front, so that if you approach the cart while the robot is running, it will slow down the speed of the robot, and if you get too close, it will actually stop the execution of motion of the robot. And if there's any other information that you need about our hardware, it's available on GennFlex's website. From a curriculum standpoint, we have our curriculum book, which you can see here. The curriculum is based around 4 different labs to give students as much hands-on time with the robots as possible. They'll be taught the skills needed leading up to each lab, and then just be left on their own with help from the instructor to solve the problems that are given to them. The instructor certification course is going to be the same course. It's just going to include training on how to operate the safety functions, along with training on how to operate our learning management system.
Well, thank you, Mark, and I hope that answers your questions. No reason to reiterate any of that. I would like to add one thing is this smart pendant. That's how students are able, that's how anybody is able to migrate through what's already in here to actually build their own jobs and have the robot do whatever application is needed based on the problems presented to them, and that's where the instructor comes in. I want you to take these blocks and palletize them, or I want you to sort them by colors. It doesn't even have to be blocks. It can be an entirely different application by changing out this shunt gripper to something else on the end effector. You can even port pneumatics into this particular arm. And that's the beauty of it. Whatever's going on, that's what has to happen in industry, in the real world. You got to break down your machines and reconfigure them for whatever that application is. The students can do the same thing here. So where do we go from here? Do we go into the labs? So at this point, we'd like to introduce you to the 4 labs that we have.
The first lab is designed to teach the students the basics of motion commands in Yaskawa's informed language. We address the standard movement types including joint, linear, circular, and spline moves. The first portion of the lab will exclusively focus on joint and linear movements, as these are the most basic and most frequently used motion commands. The lab begins with the instructor walking the students through the programming jobs that will draw simple shapes such as a square and a triangle. From there, the students will be left to figure out on their own how to program the robot to draw a star shape. The second part of the lab will cover circular and spline movements. These motion commands will be more complex for the students to program, but will give them a better understanding of how to write basic programs and what type of movements are available to them. The instructor will start by walking the students through how to program the robot to draw basic circular and parabolic shapes, and it concludes with the students using what they've learned to try and draw a heart shape. This lab provides students with an understanding of how to program command positions and the different motion paths available to reach those positions. Accurate, efficient, and appropriate movement of the robot from point to point is the backbone of all robotic programming. The skills learned in this lab are an important foundation that the students will draw from in all future programs that they write. The second lab draws on the skills that the students learned in lab number 1 and introduces new programming commands along with how to utilize inputs and outputs. The lab will simulate how the robot can interact with peripheral devices, and it will also reinforce skills learned in the first lab. The first portion of this lab is designed to give students a visual understanding of how inputs and outputs work. Using some new commands, they will create a program that allows the robot to operate a simple pick-and-place task with the I/O pendant acting as a remote control. Individual steps of the task will be executed depending on which input number is switched on. In the next section of this lab, the students will be tasked with creating a pick-and-place job where the robot will not pick up a block until input number 1 is turned on. This is designed to simulate how a robot can interact with an external sensor to know that it should only go to pick up a block if there is one available. The final part of this lab will demonstrate how to create a program that will repeat itself for as long as input number 1 is on, and skip over the second block when input number 2 is on. After completing this lab, the students should have a good understanding of how to program the robot to interact with external devices. Industrial robots are limited in what they can do without the use of input and output signals. And going forward, these skills will be utilized frequently in most real-world robotic applications. Lab number 3 is a basic palletizing exercise for the students where they will learn how to arrange blocks into a 3x3 pattern. Using more advanced motion commands, arithmetic functions, and variables, they will create a program that is able to pick up blocks from a set location and organize them into the desired pattern. Palletizing with robots is essential to speed up supply chain and production. By having the machine lift, move, and organize products, the workflow becomes more efficient. The final lab is designed to incorporate all of the skills learned by the students into one final project. They will be tasked with having the robot turn on the conveyor, wait for a block to be detected by the IR sensor, and then the robot will go and pick up each block and arrange them into a 3x3 pattern on a pallet. The final lab is designed to reinforce the skills learned throughout the course and give the students an understanding of how the material taught in this class can be used in a real-world application.
Well, now that you've seen the labs, I hope you're stimulated and as excited as we are. Again, we want to thank you for joining us. The contact information will be at the end of this presentation. And I always enjoy working with you, Mark. Thank you for your participation and everything that we do. We'll catch up with you soon.